Hello everyone, thank you very much for coming. It's great to see so many of you here today. I hope you're having a good KubeCon so far. I'm Paul, I'm from Dyson in the UK. I work as a software engineer there. And today I want to talk about infrastructure as software. There we go. So, what is this talk about? So, it's about evolving the paradigm for infrastructure provisioning and how we can transition from declaratively defined infrastructure to do so imperatively. Firstly, we'll talk about existing solutions for infrastructure provisioning, both declaratively and imperatively. We'll introduce infrastructure as software through programmatic provisioning of infrastructure, and then we'll take a look at some case studies, firstly Pulumi, and then the Amazon CDK. So, to start with, what are the main principles of infrastructure provisioning solutions? Through idempotency, we want provisioning to be deterministic and continuously yield the same results over multiple deployments. We want an agreed, centralized, consolidated source of truth for the state of our infrastructure. We want the ability to reason about desired and observed state, which facilitates such concepts as the reconciler pattern to determine state differential and rectify any drift. We want to be able to version the state of our infrastructure, enabling us to apply branching models and apply iterative changes and rollback. Through tracking changes, we can create an audit trail representing mutations in the infrastructure's desired state. Lastly, testing our infrastructure ensures that we gain confidence that changes do have the desired effect and functionality has not been compromised. To implement these principles, most existing tools define infrastructure in text-based markup languages, YAML being the favorite. So, how do we currently implement these principles? So, canonically, I'm sure everyone is aware of both of these. We'll either use Terraform or CloudFormation. CloudFormation is a first-party tool for desired state configuration management in Amazon. CloudFormation templates use YAML to describe all the infrastructure resources in AWS. CloudFormation is a powerful tool, but it demands quite some learning to master it. Moreover, it's specific to AWS, so it won't be transferable to other cloud providers. As opposed to Terraform, this is an open source tool to define infrastructure in declarative configuration files, supporting all major cloud providers and even hybrid scenarios. However, both rely on some form of templating to represent infrastructure state. But is this really infrastructure as code? Are we maximizing our development experience and using all the tools at our disposal? So, I'll just get on my soapbox for this bit. A bit about YAML and DSLs. YAML and DSLs restrict our capability to truly maximize our repertoire as software engineers. Whilst YAML is a great assembly language to configure Kubernetes and other cloud-native tools, it is not expressive enough to capture common requirements and leads to significant boilerplate and copy and pasting. Due to this, there are a few DSLs like Helm and KSonnet that aim to solve this. However, this exacerbates the issue, as this adds another level of cognitive overhead to the development experience, having to learn the nuances and maintain the behaviors of another toolset. YAML's strength is in structured data. Where it can go wrong is where YAML tries to describe behavior. Variables, arguments are not structured data. This is programming masquerading as configuration. We've met these concepts before, so why are we reinventing imperative programming? Due to the constraints of templating languages, we have a distinct lack of features like looping constructs, object-oriented principles like inheritance, abstraction, recursion, threading, automated testing, and these are all absent, inhibiting our developer experience. So, as software engineers, what we really want is infrastructure as actual code. We want to use the same language that we already know. We want to stay in the same editor and use the same frameworks and have the same developer experience. We want to leverage everyday features like auto-completion, compilation errors, and reuse the developer skills that we already have. We should come up with abstractions to generalize our code and create reusable components. We should leverage the open source community in our projects and combine our applications code with infrastructure code in a consolidated repo. So, enter infrastructure as software. The approach of programmatically defining infrastructure using familiar programming languages and toolsets. This is born out of the rapid pace of cloud-native development, combined with the shift to ephemeral infrastructure and the consolidation of application code and infrastructure code, which demands a different view of cloud development. So knowing JavaScript, Python, Go means we can start codifying our infrastructure right away. It removes one of the biggest barrier to entries around infrastructure as code as we know it now, which is another language to learn, or another toolset. Unlike Terraform or CloudFormation, we don't have that problem. Avoiding the learning curve associated with learning yet another DSL is avoiding the learning curve associated with yet another DSL is a huge value add. Furthermore, by representing our infrastructure as actual code, we get to easily add tests using frameworks we know, and the lack of testability in things like Terraform and CloudFormation at the moment has been a big bugbear, and obviously with using programming languages, we can avoid that. So, adopting this approach, we can firstly leverage software principles in infrastructure composition. Language features like inheritance, abstraction, encapsulation, recursion, looping constructs, error handling immediately power up our capabilities and productivity. We gain tighter controls when it comes to governance of our cloud environments, and having our resources specified in an application or library means that we can more granularly check and control what code and thus state changes are happening before they are pushed out through our pipelines. We can take advantage of static analysis and linting of code, and we can even start doing TDD with our infrastructure. We can have a coexistence between infrastructure and application code, where event-driven applications whose deployment and execution are all encapsulated in the same source code. So this ephemerality is often characterized as developers moving down the stack, where they're becoming responsible for infrastructure, and ops moving up the stack, where they're becoming responsible for the code. But the reality of the overall shift is towards increasingly codified provisioning of short-lived infrastructure. To support this shift, enterprises need the tools that can connect application code and infrastructure code in a way that is logical, expressive, and familiar to developers and operations teams, where application code is increasingly defines the infrastructure resource requirements of a cloud application. So we've seen this before, and I won't dwell on these because we need to quickly move on. But firstly, we've got Troposphere. So this is a Python library for creating CloudFormation in Python, which can be rendered into the appropriate YAML or JSON templates. We'll come back to this in a second when we see the CDK. We've also got GoFormation, which is orientated around bidirectional transformation of Golang infrastructure code to CloudFormation templates. Also, we've got Cloud SDKs. So these facilitate common languages to define, configure, and deploy resources across cloud providers. What is lacking with these solutions, though, is the life cycling of the components and the mechanisms to deploy, manage the declarative infrastructure. It's important to realize that these libraries give direct access to the cloud APIs. Though they can be used to provision resources, they leave it up to the programmer to do so reliably. Because these are imperative libraries, attempting to programmatically provision and update infrastructure, using them can be error-prone, usually resulting in bespoke, homegrown provisioning systems. So, to start with, let's take a look at Pulumi. So, Pulumi is a multi-cloud, multi-language cloud development platform, which is fully extensible in both its engine and ecosystem of packages. It supports TypeScript, JavaScript, Python, and Go, with SDKs for AWS, Azure, GCP, and Kubernetes. The Pulumi Cloud Development Platform is a combination of tools, libraries, runtime, and services that deliver a consistent development and operational control plane for cloud-native infrastructure. Pulumi's programming model extends across infrastructure, managed services, containers, container management, and serverless technologies, with full APIs for those services exposed, which can be targeted by any chosen language. We can build libraries of code packages when implementing standard policies, network best practices, and abstract resource configuration away from downstream services. So these are just some high-level examples. So we see here that we're provisioning an EC2 instance using the AWS library and setting the configuration through the parameters in the constructor. We can export and import values between stacks, enabling portability between environments. More on the Kubernetes integration to come, but here we're just defining a deployment, as all the objects within Kubernetes are first-class citizens within Pulumi. We also can define event-driven applications where infrastructure and business logic coexist and work together to form powerful serverless applications. And Pulumi also offers a cloud-agnostic library to deploy infrastructure to any cloud-native environment, abstracting away the underlying cloud implementation and facilitating applications to be cloud-neutral, portable, and therefore driven by business logic instead of stating any cloud-specific provisioning. Pulumi supports multiple backends for storing its state. The two primary kinds are web, which is a backend accessed through CLI and REST calls, and secondly, the file system, which is the backend stored locally on the file system. By default, the CLI uses the web backend hosted at app.pulumi.com. The web backend stores all checkpoint state securely, and CLI always communicates directly with the cloud providers using client-side authentication, and all state is encrypted at rest and in transit. So just to compare Pulumi to some known solutions, so Terraform is the closest comparison to Pulumi. In Terraform, we'll declare infrastructure in a DSL, and the Terraform engine takes care of provisioning and updating resources, very similar to Pulumi. The major differences, though, are firstly the use of languages. So as I said, in Terraform, we have to declare our infrastructure in DSL or HCL. In contrast, Pulumi lets us use the languages that we already know, and we get the added benefit of the features of those languages. So like I said before, things like looping, functions, classes, abstraction, etc. In regards to CloudFormation, so again, we've got the added benefit of using languages as opposed to reasoning about infrastructure as templates, but also Pulumi is multi-cloud. So we can easily manage resources from different clouds, easing what would otherwise require manual orchestration. And in regards to cloud SDKs, the cloud providers offer SDKs in multiple languages, like Boto in Python, so there's that similarity. But it's important to realize that these libraries are different in their aim. These libraries are hitting the cloud APIs and provisioning the resources, but leave it up to the programmer to do so reliably. Yeah, and as I said before, it's kind of up to us to ensure that that is done successfully. So a little bit on the Pulumi Cloud. So the Pulumi Cloud is a framework within Pulumi for building container and serverless applications in a cloud-agnostic way. So the Pulumi Cloud framework is in preview and provides abstractions that will allow us to write a cloud application for many different cloud providers using a common API. This is an abstraction package that defines the APIs common to all cloud providers. Because these abstractions allow us to operate over different cloud platforms in a consistent manner, low-level functionality and capabilities of individual platforms are intentionally not exposed. So just to take a look at an example, so the service type in the cloud library expresses a load-balanced container, which can be targeted to run in multiple cloud providers. We also have the API type, which exposes serverless functions over HTTP. The package also offers simple data abstractions with cloud-agnostic resources, like tables and buckets. So for Kubernetes, so Pulumi offers a SDK for Kubernetes and allows us to write Kubernetes applications in the language of our choice, and it's designed to fit anywhere that Kubernetes is already being used. There is API parity with Kubernetes, so users don't have to learn a new API to write Kubernetes applications in Pulumi. It's compatible with existing YAML and Helm charts, and is supposed to be a drop-in replacement for kube control apply. So wherever you have a kube config, you can use Pulumi. In addition to this, there are multiple benefits from using Pulumi to orchestrate Kubernetes. So firstly, we have proactive reporting from errors if resources fail to initialize. So if Pulumi is able to deduce why something failed to be created in the cluster, it will obviously fail that, and therefore no more digging around in the cluster to ascertain what happened. There's also drift detection, so Pulumi can offer a diff between the detected state and anything that's out of sync with the spec in version control. There's precise lifecycle tracking, so like Terraform, the plan phase will explicitly tell us which resources will be updated and deleted by an update. There's end-to-end planning, so when we make a change to our cluster, we're told how that change will propagate around our resources. So for example, if we change a config map, it will tell us which pods will be affected by that update. There's strong integration with managed Kubernetes offerings, so we can provision clusters in EKS, AKS, and GKE. And we can also provision resources directly in that provisioned cluster, which we'll demonstrate shortly. And lastly, the Kubernetes SDK also supports deploying Helm charts. So this is possible through chart repositories or assuming local charts on the file system. So this is just a simple example. So the full API of Kubernetes is available just in code, not YAML. So akin to normal Kubernetes resources, We have a deployment specification which can be declared, and then these resources are first-class citizens in our languages. Here's a simple Nginx deployment with a service of type load balancer, and the load balancer's hostname is then exported from the stack and can be used via the CLI. So if we deploy the stack using the Pulumi up, we see a preview of the resources that get created, as well as their readiness as they become available in the cluster. Cool. So, taking the Kubernetes guestbook application, we can refactor this from being quite a verbose set of resources and take advantage of being in an environment which provides abstraction. We can recognize a common pattern for a deployment, followed by a service which exposes that container, optionally behind a load balancer with a stable IP. This can be abstracted into a class which defines all these common components and can be instantiated to create multiple objects, thus aiding component reuse and reducing repetition. The end of this is we have 3 deployments and 3 services, with the front end being load balanced, which is the same. However, we've gone from the 147 lines of YAML to approximately 20 lines of code. Not only that, but the code is much simpler to understand and easier to maintain. So the base class of this creates the deployment and service objects and exposes the IP of the service through any, which is obviously in the scope of any instantiations of that class. So a Pulumi preview shows all these resources which will get created in the cluster. Cool, so moving on to managed services. So Pulumi's Kubernetes integration can be taken further by provisioning clusters via managed services in cloud providers. So provisioning and managing and monitoring Kubernetes clusters is no easy task. In AWS, we can use EKS to ease a bit of this burden, but it's still difficult to get up and running end-to-end in code. However, through the Pulumi EKS support, we can aid this task and get a cluster provisioned using minimal code. The EKS component takes care of setting up all the resources and configuration needed in an EKS cluster. So we'll get the EKS service role, we'll optionally get a new VPC, we create the control plane, we get the worker nodes in an ASG, which will then automatically join the cluster. We get a config map, which allows the EC2 worker nodes to join. We create a storage class in the cluster to allow provisioning EBS-backed persistent volumes, and we then construct the kube config, which is needed to access the cluster, and that can be exported and therefore used on the command line via kube control. So here we see a preview of the EKS stack with all the resources that will get created. So yeah, this will end-to-end provision an EKS cluster with worker nodes for us. By exporting values in the stack, we can see references to these values and use them in the CLI. This is the instance of programmatically taking the generated kube config from the EKS stack and using it to access the cluster via kube control. Note that we didn't have to populate the kube control here with any ARNs or IAM credentials, as that's all injected by the EKS library during the provisioning time. Cool. So on top of Kubernetes, we also have support for Helm charts. So this significantly reduces the amount of boilerplate code required to deploy Kubernetes, to Kubernetes, deploying from chart repositories or local charts on the file system. Tiller is not a requirement, although that obviously won't matter as of Helm 3. But Pulumi will expand the Helm chart and submit the expanded YAML to the cluster. Here we're deploying the Jenkins chart from the stable repository and exporting properties from the created resources. So running Pulumi up, we see all the Kubernetes resources that will get deployed via this Helm chart, along with their readiness. Taking the exported endpoints, we can navigate to the front end via the load balancer's hostname in AWS. Cool. OK, this is where we go slightly overboard. But given that we have support for Helm charts in Kubernetes, our repertoire is expanding significantly to include CRDs, operators, and entire supersets of functionality like service meshes. So through referencing local charts and value YAMLs, we can programmatically deploy things like Istio along with configuration for our cluster and assert on each component's readiness, stability, and functionality. So here we're just taking a local instance of the Istio chart as well as the values YAML and deploying that to them. So if we do a Pulumi preview, we see that it creates quite a few resources in our cluster. But what we've done here is programmatically deployed and configured an entire installation of Istio with lifecycling to assert that all the resources was created successfully and that we have versioning and rollback of our stacks. Whilst this might be a bit of overkill, it nevertheless demonstrates the possibilities of deploying resources to Kubernetes via Pulumi. So one major advantage of having infrastructure as software is that serverless offerings like AWS Lambda, Azure Functions, and Google Cloud Functions can be real language lambdas. Serverless offerings today divide the developer experience between infrastructure, which can be provisioning the Lambda runtime itself, and writing and maintaining the code that will actually execute in the function itself when triggered. Because we're using general purpose languages, we can create resources and then wire up event handlers just like normal event-driven programming. You can create event sources and handlers in the same program, choosing to wire functions to existing resources. The optimum way is to create functions inline. This blurs the line between infrastructure and application logic in a way that makes programs feel like first-class distributed apps. So here we've got a couple of examples of this. So we just create an SQS queue, I believe, and a bucket, and then we've got some onX methods which can be used on these resources to register event handlers. So for the most part, any code we write here will actually will work, unlocking all sorts of powerful compositional scenarios. Underneath those onX methods are many AWS resources transitively created like IAM attachments to facilitate the invocation of event-driven workloads. So just a bit of a segue into testing. So why should we be interested in testing our infrastructure? Firstly, it increases our confidence that any changes introduced to our infrastructure are actually going to be functional. It improves resilience and security and demonstrates a left shift to address code quality, security concerns, and environmental consistent deployments. Through the varying levels of inspection, we have a variety of options available to derive assertions of functionality and conformance to SLAs, security criteria, and best practices. As we see, there's a broad spectrum of infrastructure testing options available. However, we could say that some of these are retrospective assertions of the state of our infrastructure, and we can use Pulumi to complement this and expand on some of these mechanisms. So, as we're able to use languages like JavaScript, TypeScript, and Python and Go, we have the full power of each language available, including access to tools and libraries for that runtime, including testing frameworks. Because we obviously might have functions in our code now to say that we want to tag resources or define some event-driven workload, we probably want to test them or do TDD. Because this is the same as writing ordinary unit tests against any program and our choice, we can, for example, use sort of well-known libraries. And here we're creating an EC2 instance with a security group and associated ingress rules. Once we set up our environment and stack, we can assert against attributes therein. Here we're just making sure that each tag is not false and not missing an entry for the name key in the map. Also, we can make assertions about the security of our code and assert that we are conforming to security best practices. Here we search through all the ingress rules in the associated security group and make sure that we don't allow overly permissive SSH inbound access. Cool. So just to close up on Pulumi. Firstly, cloud agnosticism provides flexibility and portability. It means we avoid vendor lock-in, and in some cases, we can run our stacks in multiple providers by changing external config and not changing the source code. The Kubernetes cluster provisioning using managed service integrations reduces the cognitive overhead and code footprint and management of resources to a minimum. Programmatic generation facilitates more granular control and inspection of infrastructure resources. And lastly, abstraction aids standardization across organizations through reuse by downstream services. So next up, we have the Amazon CDK. So the Cloud Development Kit is an open source software development framework to define cloud infrastructure in code and provision through AWS CloudFormation. The CDK is currently in developer preview and can be implemented via Java, JavaScript, TypeScript, .NET, and as of recently, Python. The CDK is basically a wrapper around CloudFormation, which abstracts CloudFormation definitions of AWS resources into an object-oriented library. This allows us to define high-level abstractions of resources which can be easily reused. The CDK is a command line tool for interacting with CDK apps. It allows us to synthesize stacks into CloudFormation templates and deploy stacks to AWS environments and diff against deployed stacks to understand the impact of code changes. The construct library includes a module for each AWS service with constructs that offer rich APIs that encapsulate the detail of how these should be used and reduces the complexity and glue logic when integrating various AWS services. So we can think of the CDK as a cloud infrastructure compiler. It provides a set of high-level class libraries called constructs that abstract AWS cloud resources and encapsulate AWS best practices. Constructs can be integrated together into object-oriented CDK applications that precisely define our application infrastructure and take care of the complex boilerplate logic. When we run the CDK application, it's compiled into a CloudFormation template, which acts like the assembly language for AWS cloud infrastructure. This template is then ready for processing by the CloudFormation provisioning engine for deployment into our AWS environments. Again, because the CDK supports object-oriented languages, we can utilize language features like looping, abstraction, inheritance, and do some testing. So, as mentioned, the CDK has support for well-known languages. So, to get started, we can instantiate a new app or construct library in the language of our choice. Here we see a couple of examples of how constructs can be instantiated with resource configuration passed into the constructors with the specific granularity required. With both these resources in scope, we can alter their behavior, perform operations, create associations, and retrieve instance attributes for particular resources. Here we see the command line available to interface with our stack. So we have CDK synth, which will synthesize our source code into a CloudFormation template. We've got CDK deploy, which will take that synthesized CloudFormation template and deploy it into our AWS environments. And we've got CDK diff, which will monitor any state drift between the last deployed state and the current state of our stacks. Here we've just got a simple example of an app. So on the left, we've got the application, which instantiates our stack. In the stack, we define a couple of resources and instantiate the construct. And then we have some behavior in the construct, in this case, creating a few S3 buckets. If we run CDK diff, we can see the state of the current stack, which in this instance doesn't exist, and it will show you all the resources that will get created. So, testing. As we defined our stack in this case Python, we can leverage common testing frameworks. So in this instance, we're using unit test and just invoking our test stack and testing whether we've actually got the correct behavior therein. So in terms of serverless, what we're able to do is have infrastructure and application code living together in the same repository. So here we're defining a Lambda in our stack, and we're having the actual implementation read in from just a Lambda handler, which is in the same repository. This could be inline, so we have a kind of coexistence between the infrastructure, which provisions the Lambda, and the actual workload that will get invoked in that Lambda. The beauty of doing this, though, is that the CDK will auto-generate any resources required to facilitate the deployment and functionality of the desired stack. So deploying that Lambda, in this instance, we have an IAM role, which is created and provided to the Lambda resource, providing it with the basic execution capabilities. If we deploy that, like most sort of provisioning systems, we get sort of the readiness of all of our resources, very similar to how CloudFormation renders it in the console, and yeah, how successful that deployment was. The CDK also provides an assertion library containing helpers for writing unit tests and integration tests for CDK libraries. Using this library, we're able to assert that certain behaviors or features of our application and stacks are true before we actually deploy that infrastructure. So firstly, we can inspect stack templates to assert that they contain the expected resources and associated properties, and that synthesizing has not compromised the behavior of the stack. Here, we're more orientated around the stack security compliance and network configuration. In a high compliance environment, we may have specific requirements, which, as demonstrated here, can be checked at the code level before any deployments occur, thus safeguarding the integrity of our stacks and environments. So, through the construct library, the CDK exposes an abundance of resources and managed services. One such resource is EKS, which, from experience, requires a bit of orchestration and configuration to provision from code. So moving all that provisioning into the CDK allows for greater control over the specific behavior of the control plane and worker nodes in AWS, and also aids in integrating all the different components together. So for the worker nodes, we can do a diff and show us all the resources that will get created. So this goes ahead and creates the ASG of the worker nodes and exports the ARN required for them to join the management plane. So again, having constructs in code means that we can instantiate them and test against their behavior. This, again, allows us to have assurances that what we deploy is going to function as desired, and also gives us confidence that any changes being made in our code won't compromise functionality. So just to round off on CDK. So again, provisioning EKS in code is much more reliable, and we can reason about the actual observed and desired state of our clusters. There's no native Kubernetes support, so we're still reliant on a bit of glue to actually get the cluster working end-to-end. And as I said, the CDK is still in kind of developer preview, so Python's come along recently, so there's just a kind of ongoing effort to get SDK parity in the different languages. And there's some links to check out if you're interested. So just to round off, a bit on cultural readiness. So when we're seeking to shift the paradigm for infrastructure composition into programming languages, we need to first make sure that the surrounding culture is one which is ready for this to be adopted in. If there are DevOps silos or distinctions between infrastructure, platform, and development, then introducing a principle which essentially blurs those lines needs to be carefully considered. Whilst it might be acknowledged that there are distinct benefits to shifting developers down the stack and ops up, this might actually be detrimental in a culture which is not ready for multidisciplinary teams and organizations. Depending on the cloud-native maturity of an organizational culture or technology offering, there may be certain prerequisites required before leveraging the value of ephemeral environments and codifying cloud resources. There is an evolution through the cloud-native maturity paradigm, where we must have stable foundations and have invested and culturally appreciate these stages of our evolution. Without this, we won't maximize our potential, nor deliver the full value of running in a truly cloud-native environment. So, to wrap up, hopefully this has shown everyone the benefits and justification of moving infrastructure code to a more imperative style and how that change in paradigm can be achieved. We have the tools to evolve the paradigm of infrastructure composition, which facilitates a coexistence of application and infrastructure code, thus resulting in more testable infrastructure. This reduces the cognitive overhead of YAML and DSL development and leverages modern language features to programmatically define cloud resources. As application code and supporting infrastructure become more and more blended, it's natural that software developers take the responsibility to define both. The next logical step is to use the same set of languages, tooling, practices for both software and infrastructure. And that's everything. Thank you very much.